So we want to discuss angles in radian, arc length, area of a sector, and angular speed. When we were defining the radian value for an angle, we discussed that it's related to the length of the arc on a unit circle that theta is facing. This is a fine definition, except that we have to have in mind that this length is unitless, and we cannot use any units for that one. Generally, the definition, the actual definition of the angles in radian comes from the same logic, but the formula that the logic brings to you. So usually when we're discussing the angles in radian, we're defining it by pi times the angle in degrees divided by 180 degrees. And the radian value is unitless again. So the definition that we used, or how we discussed it in the beginning, just gives you the logic behind how it works. Now we want to discuss the arc length and area of a sector. Let's say that we're not in unit circle anymore. So here we're still in unit circle, or could be outside the unit circle, but in any way the formula follows that way. Here R, and it could be anything, it could be 1 or it could be any other value. And I want to see if in this circle the arc length that is facing angle theta. How do I compute that? If you go back to the unit circle and sort of the logical definition, not the formal definition, but the logical definition that we defined, we discussed that this arc length is is equal to theta. Now, in here, using that same logic, since the radius went from 1 to r, everything has to blow up or shrink by r. Therefore, the arc length should be r times theta. That's one way of discussing this. The other way of discussing this, so this is method number 2 of driving the same formula, basically, is that the arc length that theta is facing to the entire circumference of so the arc length, the ratio of the arc length divided by the entire circumference of the circle, which we know is 2 pi r, is equal to theta divided by 2 pi. So theta divided by 2 pi, that's the ratio of theta over 2 pi is the same ratio as the arc length to the entire circumference. That's another logical way of driving the same formula. And then the 2 and 2 simplify, pi and pi simplify, so you end up with arc length equal to r theta. So that was the method 1 using that logic, and this is the method 1 using the logic of what's the ratio between them. In here, we're trying to figure out the area of the sector. So the area of the sector that theta is basically it's like a slice of a pizza. So the area of that slice of the pizza, where the angle of that slice is theta, what would that be? And this one again, we use the second logical method of driving the formula this time, and this is theta, the ratio of theta to the entire, the area to the entire circle is the same as the theta to entire full rotation. So theta over full rotation, this ratio, full rotation is 2 pi, should be equal to the area of the sector divided by the area of the entire circle, which is pi r squared. Now we want to simplify everything. Here pi and pi simplify, and then I get area of the sector is theta times r squared divided by 2. Theta r squared divided by 2. So this is the discussion of the angle, the arc length, and area of a sector. The next thing is the angular speed. What is angular speed? Angular speed is the, and we show it with omega, is the angle. This is the average angular speed is equal to the angle that has been covered divided by the time that it was covered in. So omega is equal to theta divided by t. The next thing is how can I relate this to the actual speed? Remember, when you're trying to go in a circle, the distance you're traveling is the arc length. So basically, v is equal to the arc length divided by t. That's the average velocity, and v is going to be, what is arc length? Arc length is going to be r times theta divided by t, and I'm separating r. I'm bringing r outside the fraction, so it's equal to r times omega, or r times the angular speed. Those formulas are useful in your physics courses. And we're done with this section.